Now let us see the reactions of these amines with Carros acid. Carros acid is H2SO5. If you want the structure of it, I'll draw it for you, where you have two double bond O, S double bond O's, you have OH here and OOH here. Now this Carros acid will give you H2SO4 and nascent oxygen. So if you are treating this with amine, indirectly you are supplying oxygen to it, that is, you are oxidizing this. Now in the first step, on this carbon you have two hydrogens, and when you add 1 mole of this nascent oxygen or H2SO5, this is going to take two hydrogens, one from this carbon and one from this nitrogen, and you are going to get a double bond, which is C double bond N plus water you got. Now if you treat it with one more nascent oxygen, since you are supplying H2SO5, you have plenty of nascent oxygens available. Now you are going to get OH on this nitrogen, that is, this H is getting converted to OH. Now if you treat it with one more nascent oxygen, the hydrogen which is present on this carbon is getting converted to OH. Now if you carefully observe, first you have two hydrogens on each carbon and nitrogen, then you have only one hydrogen on carbon and nitrogen, and then you have one hydrogen on carbon and 0 hydrogens on nitrogen, and then you have 0 on carbon and 0 on nitrogen. Now what happens if you treat it with a secondary amine, say R2NH? Now for this secondary amine, you are going to get this one directly. This is what you are supposed to remember, because there is no special prescribed mechanism for it, and it is there, but for your level it will be very difficult to understand because it involves a complicated mechanism. Now for tertiary amine, now this is very important one actually. If you treat it with nascent oxygen or H2SO5, you are going to get this compound which is called amine N oxide. It has a positive charge on nitrogen and negative charge on oxygen. Now these reactions are very important, and what are the consequences of it and what happens if you heat it, we'll see in the problems. Now that we are done with the reactions with aliphatic compounds mostly, now let us see the particular reactions or specific reactions with aromatic compounds. In the aromatic compounds, mainly we'll be dealing with aniline. First, let us see what are the properties of this. You know that this NH2 is ring activator group and ortho para director group. This is because this nitrogen donates lone pairs to the ring. Now, if you treat this aniline with Br2 in the presence of Fe or Br2 in the presence of H2O, which is bromination reaction basically, you are going to get a white solid, which is you have Br substituted at ortho and para positions. All the ortho and para positions are blocked, that is, or filled by Cr or Br, that is. Now the electrophile in this reaction is Br plus. Now just remember this from your benzene chapter. So here, as you can see, you got a tribromine substituted product. What if you want only ortho or only para? For that, what you do is you treat this aniline with first CH3 C double bond OCl in the presence of AlCl3. Now if you carefully observe, you may think this to be the acylation reaction. It is actually acylation reaction, but not on the benzene ring. That is, it is not Friedel-Crafts acylation. It is just acylation on this nitrogen, where you have one hydrogen replaced with C double bond OCH3. That is, this nitrogen donates its lone pair to this electrophilic side. So this bond shifts in this direction. You're going to get negative charge on this. But you know that oxygen is not good leaving group. So this bond comes again. And you also know that Cl is good leaving group and this has lone pair. And this can donate to this AlCl3. So you're going to get, on leaving this Cl, you have this one and AlCl4 minus. As you can see, the lone pair on this nitrogen here is in cross conjugation. That is, it is in conjugation with this C double bond O and this phenyl ring. So because of this, the electron donating capacity of this nitrogen to this ring has comparatively decreased than the aniline. So it is less ring activator when compared to aniline. So when you treat it with Br2 in presence of Fe or Br2 in presence of H2O, you are going to get either on both ortho and para positions. This is ortho and this is para. And if you hydrolyze it, that is treating with H2O in the presence of an acid, this will undergo hydrolysis. So you get H here, OH here, and also H here, OH here. So you got your acetic acid back. You got your acetic acid, and you also got a para product and an ortho product. Now this reaction is called Schotten-Balmer reaction, which we use mostly for this preparation of para or ortho products. Now in the next part includes acylation reactions. As we have told in the previous reaction, this acylation is indicating the C double bond OCH3, which is acyl group. That is, introducing this acyl group to this NH2 is just acylation reaction. So you treat it with acylating agent. Remember that the solvent which you are using here is pyridine. It is non-aqueous solvent. There is a reason for that, because if you use aqueous solvent, if aqueous is used, then this will undergo hydrolysis. That is H here, OH here, and this reaction favored backwards, so you are not going to get the product. So we use pyridine here, which is non-aqueous. Next important reactions regarding aniline are nitration and sulfonation. Now all these reactions were taught to you in your benzene chapter. Once go through that, you will be through with it. And also refer to your NCERT for the percentage of ortho product and the para product, and also in some cases meta product uptime. Now also you just see the Friedel-Crafts reactions. Now the another set of reactions include the reactions of diazonium salts. Now this one is called a diazonium salt. The structure of it would be in this way, where you have a pH, and for it you have a structure like this one, or you may also have a structure like this one, where you have double bond N, positive charge, and X minus. Now whenever you treat this with CuCl2 in the presence of HCl, or Cu2Br2 in the presence of HBr, this is Cu2Cl2, you will get ArCl or ArBr correspondingly, as you use HCl or HBr. Now this reaction is called as Sandmeyer reaction. It's a very useful one. And next reaction includes Guttaman reaction, where for the same diazonium salt you treat with copper powder in the presence of HCl or HBr, you are going to get ArCl, that is this one. Now next one is, if you treat the same diazonium salt with Ki, you are going to get ARI. Also, if you treat with now, regarding this ARI, if you observe, it is not so easy to prepare ARI with direct iodination of benzene. This is because iodine is large size, and so attack on the benzene ring is not favorable for it because carbon atom has small size. That is, effective overlap is not possible. That is, overlap is not effective. Here there is overlap. The overlap here is not effective. But as you can see, with the help of this reaction, you have got ARI. Now, you are told that in the benzene chapter, you will be taught in the Benz-Kiemann reaction how to include fluorine to the benzene ring. That is this one. You are told that this is highly exothermic if you directly prepare it from this fluorination of benzene. That is, if you use fluorine in the presence of any Lewis acid, you are going to get this one. But you are told that this reaction is highly exothermic. So the reaction vessel in which you take it gets heated up, and so it is not so easy to carry out this reaction. But there is an alternative way through this reaction, where you have treated this diazonium salt with fluoroboric acid. You are going to get a complex like this one, and finally you are going to get ARF, or this structure. Now next reaction includes addition of hydrogen to the rings, that is substitute. That is, like say you have a diazonium salt like this one. If you supply acid medium to it, that is H plus to it, you are going to get benzene. The mechanism for it is taught to you in your benzene chapter, where you have told the same thing for decarboxylation and also in desulfonation. You are taught this in the solved examples of benzene. Once quickly go through it and you will come to know what exactly it is, or Cl minus it is. Now here the electrophile is H plus. This attacks here and this leaves. So you are going to get that. Now revise the mechanism through in the benzene chapter and you will have a lot of clarity in it. Now the next one is addition of NO2 to the ring. So here also we are doing the same thing. We are starting with a diazonium salt, say AR2 plus Cl minus, let's say, and you have treated this with fluoroboric acid. You are going to get this compound, say. Now this is same as up to here. Now if you treat this with say NaNO2, then you are going to get PHNO2. Now these reactions have got a lot of importance because the substituents which these are including, like say F, Cl, I, NO2, these are not possible to directly attack to the ring. That is, direct substitution of these compounds to the ring is not possible. But because of help of this diazonium salt, the substitution to this of these compounds to the benzene ring is feasible. So these compounds have got a lot of importance in an industry, or if you take. Now let us quickly go through the solved examples of it and see what patterns can be asked in the amines chapter. After discussing the theory regarding the amines, let us move to the problems, where in the first question we are asked to discuss the mechanism for the two reactions, where the first one is Gabriel phthalimide synthesis and the second one is Hoffman bromamide reaction. Now there is a question that first, to solve this you must know what the reaction is. First, let us try attempting the Gabriel phthalimide synthesis. In the Gabriel phthalimide synthesis, first you start with terephthalic acid, as shown this one. We have 2 C double bond OOH, and if you treat this with NH3 or ammonia, let's say, at high temperature, now this dehydrates and this also dehydrates, and you are going to get a compound like this one, where you have C double bond O, C double bond O, and H here. Now if you remember, after obtaining this you have treated this with base, say NaOH. Now this base takes this acidic hydrogen. As you can observe, it can also undergo substitute here, which is electrophilic site, but since we have acidic hydrogen and acid base reactions are faster, it first prefers this hydrogen. Now you got this one, where you have C double bond O, C double bond O, and N minus. Now if you remember, for this you have treated with RX. Now this is where substitution is taking place. If you remember from the theory where we have told you, this is SN2 attack. Here you have got a nucleophile with negative charge on nitrogen. Now this nucleophile attacks on this R, leading to the departure of this X group, and you are going to get this compound. You have C double bond O, C double bond O, N, R. Now what you have done is you have subjected this to hydrolysis. H3O plus, say, in the acidic medium. Now on doing this you have got this hydrolyzes to give hydrogen here, OH here, hydrogen here, OH here, and you are going to get back your terephthalic acid, where you have C double bond OH, C double bond OOH, and you have got an amine. Now as you can see, you have started with ammonia and you ended up getting a primary amine. Also carefully observe that you have SN2 attack here. That is why we have told you that all the conditions favorable for SN2 are favored for this reaction. Remember carefully. And one more thing is that secondary or tertiary are not obtained here, and this substitution is not possible if R is pH group. This is because directly at ordinary conditions this substitution is not possible at ordinary conditions, remember. Now also see that the first part is this dehydration, where removal of water. Now the mechanism for this is, first this lone pair which is present here attacks on this electrophilic site, leading to the departure of this group, and we have not shown that here, and this OH obviously takes hydrogen from other and you are going to get water, so directly we have shown it as in this one, these boxes. So Now let's discuss the second reaction, which is Hofmann bromide reaction. The reaction for Hofmann bromide reaction is, we have amide for initially, and you have treated this with Br2 in presence of NaOH or any base, and you have got a primary amine finally. Now let us see how this happens. And remember, in the first case we are adding base, which is NaOH. This mostly acts as base if there is acidic hydrogen. If not, it acts as nucleophile. Now, as you can see here, this hydrogen is acidic because if say this OH minus takes this hydrogen, you are going to get R C double bond O NH minus, and carefully observe that this is in resonance with this C double bond O. That is, the one of the possible resonating structures is O minus double bond C NH. Now, the compound which you have got has negative charge on nitrogen. It acts as nucleophile. Now you have got bromine in the mixture, Br. Now this nitrogen attacks on this bromine and leading to the departure of this one. You know that in the presence of this polar reagent, this being homolytic, instead of undergoing homolytic cleavage, undergoes heterolytic cleavage, because in the presence of this one, the bond has partly shifted towards this bromine, that is, it has acquired partly delta minus and it has partly delta plus, and you are going to get R C double bond O NH Br. Now you have got in this molecule one more acidic hydrogen, and here what happens is, first OH minus takes this acidic hydrogen. Again you are going to get the similar molecule like C double bond O N minus with negative charge on nitrogen. Now you may think that this will give you with Br2 R C double bond O and Br. This is what we generally expect by following this step, but this is not observed. This is because if you carefully observe, here you have two bromines on one nitrogen which undergoes severe repulsions because these bromines are large size. So this step won't occur here, and here the crucial step which is going to occur is this shifting here, and since it is polar, oxygen get negative charge, and one more thing is that oxygen is not good leaving group. So this bond again comes back and leading to the departure of this R group, and this R group attacks on this nitrogen leading to the departure of this bromine group. So you are going to get O double bond C double bond N R, which is alkyl isocyanate. Now you have subjected this to hydrolysis. Now let's look into the mechanism for this hydrolysis. First you have acidic medium and you have got alkyl isocyanate. You have got H plus in the medium. You know that nitrogen has lone pair and also oxygen has lone pair, but since electronegativity of nitrogen is less than electronegativity of oxygen, nitrogen donates its lone pair more effectively than oxygen. So it's going to donate its lone pair, and you are going to get O double bond C double bond N H R, positive charge on nitrogen, and this nitrogen is going to take away this bond, and you are going to get O double bond C, positive charge on carbon, and H R. Now you have water in the medium, and you have treated this and not treated. You have got this one, OH2 NHR. Now this will give you O double bond C OH NHR. Here also the same thing happens. This nitrogen donates electrons to this H plus ions, and you are going to get O double bond C OH NHR H plus, and it's going to take away this bond again, and you're gonna have O double bond C OH, positive charge on carbon, and R NH2, which is a primary amine. Now you have got water. It donates its lone pair to this carbon, and you are gonna get O double bond C OH OH2. Finally you are going to get this compound. Now you know that 2 OH groups on 1 carbon is highly unstable. So as done in the previous cases or in the previous chapters, this dehydrates to get CO2. Now there is a reason behind discussing this mechanism and these questions, because you are supposed to know the mechanism for any reaction which you are learning. And if you see, for this hydrolysis reaction, you can also be given the solvent as D3O plus. Say here you can also be given as D3O plus. Now you can solve it only if you know what is happening here, that is the mechanism of it. Now let's go to the next part of this.